Okay, let's go for yesterday. Yesterday, there are a lot of things. Okay, I will give you examples for the eigenvalue and the eigenvector stuff, which is important that for all eigenvalues you could have eigenvectors, and they are a space called eigenspace. These vectors could be very useful in physics and also in mathematics and numerical computing. I say numerical computing in the meantime you are not programming or doing anything. Everything that is here is just so chemists and physicists using the mathematical terms without discipline. So we always think about matrices, but the matrices are operators, they are functions, transformations, blah blah blah. So these definitions and thesis that explained yesterday was just to all of this non-disciplined or not so strict using of these terms. Skip because I will give you exercises. I mean, we will do exercises. Okay, which is nice. Triangular matrices. All diagonal matrices are triangular matrices, and you know the triangular matrices and diagonal matrices has very nice features. For example, the determinants are the product of the elements in the main diagonal. That's very nice. The inversion for diagonal matrix is easy. For triangular matrix is not so easy, but it's simpler than anything. This statement say the eigenvalues of the triangular matrices are the elements of the main diagonal. It's truly and simply true for the diagonal matrices, but it's also true for triangular matrices. So that was some description about this. However, for any matrix, I mean square matrix, that has the rank of n, I mean nth order or whatever, it's true the following statement. The determinant of any matrices are the product of all eigenvalues. There is something that we never seen, that is so-called trace. The trace is the sum of the elements of the main diagonal. And for all matrices, the trace is the sum of the eigenvalues. Okay, this is just, I go quickly for what we had done. This is also something interesting. Eigenspace of a very simple 2 times 2 symmetric matrices. All eigenvalues of these symmetric matrices is real. They set have two identical eigenvalues if it's this form. It means it's an identity matrix multiplied the number. And I always, okay, yes, and if this type of matrix has two eigenvalues, then the eigenvalues are orthogonal to each other. It's for 2 times 2, but it's something general. Okay. A matrix is invertible if there is no zero eigenvalue of the matrix. If you recall this, the determinant of a matrix is the product of the eigenvalues. If there is 1 0, then the determinant is 0. If the determinant is 0, then the matrix is not invertible. Okay? Yes. Okay. Here there are more. If there is a general and it's not general, it's a symmetric n times r square matrix, and then the eigenvalues are real. If it's skew symmetric or antisymmetric, then the eigenvalues are imaginary. And have you learned the complex numbers? You have learned
the
complex numbers.
Yeah, in mathematical analysis.
Yes.
Yeah.
Yes. Okay. Here I always say the elements are real. The elements are blah blah blah. No, these are general. So the elements of the matrix could be complex or more. The block matrices are actually matrices which has elements of matrix. The matrix is more complex than a complex number. And in quantum mechanics, you have the spin. You know spin?
Mm-hmm.
You know the Pauli principle.
Yeah.
Okay, so in quantum mechanics in physics, the spins are represented by so-called quaternions. The quaternions are hyper-imaginary numbers. It has a real part, an imaginary part. Good morning. I just repeat what we talked about yesterday, so it's okay. But you have a very nice stuff for you for today. There are two other third and fourth components. Their square is -1, and if you multiply these second, third, fourth imaginary part, then you got two of them, you got the third. So this is called quaternio. It's not officially a material, I just explain you that's possible. But here this was too much because here I used complex eigenvalues and a lot of things, and it's too much. Now, this is the very solo algorithm. Perhaps you can pronounce it better. Do you speak French? No? No. Where are you from?
Ghana.
Ghana. What is the official language of Ghana? English. Yeah. This is what did you learn in school in English or in your own language?
In English.
In English. From primary school. And how many languages do you have in your country? How many languages do you have?
About 37 languages.
And are they official or you cannot use it in offices?
It's only English because we are colonized by the British.
Yes, I know, but I didn't know. I moved to France in 2008, and it was very rare. I had a colleague from Togo, and that guy, I asked him, why is it so difficult to speak English? Because the official language in Togo is French. Then it was a part of cultural shock. And then he explained the same. They were colonized by Frenches. He had his language learned from mother tongue, and also he spoke other languages. But the official language was French, and he studied everything in French in primary school. This is a big advantage, actually. Here we are closed in our language. If you are, for example, you speak Ukrainian, then it's easy to learn Slovakian. There is not so much difference between Slovakian and Czech. And the Czech usually listen to the Polish television, and the Polish listen to the Czech and Slovakian television. So these people understand each other. And it's not possible. In our language family, the closest relatives are not the closest. The closest are so-called Chanty-Manshi, and they are in minorities in Russia, somewhere in Siberia. But the big other languages are Finnish. But I don't understand Finnish. I just have a right pronunciation, and I know the grammar, and we have a few hundred common words. So it's okay. This one. Yesterday I had told a lot of things. It is in your syllabus. I don't know why. This is much more complex that we could understand, and it's much more complex that you could use. The guy who wrote the syllabus has left the university, and I cannot reach him. Actually, I know where is he. I know his email address. I have sent him emails, but he never answered. Okay, great. Actually, it's okay because he has left the university, and he doesn't get money for any advice. So this algorithm has a story, and this is not an algorithm. It is a method, and whoever developed it, then there was this Solo or someone else, another French guy, who improved it, and there is Fabre, or I don't know how to pronounce, who did something. So in Wikipedia I find this Fabre Leverrier method, but not algorithm, because this Leverrier was lived in the 19th century, and there was no computers on that time. So it's perfectly useless. I wrote this down. You cannot see it in copy-paste. This is copy-paste from Wikipedia. You can check it if you need, but I will not do anything. But Leverrier was considered as a mathematician, and this guy worked in the Paris Observatory, and he discovered the Uranus. So he was not stupid. He was a very good guy. That's okay. You know that 5 planets are visible: Mercury, Venus, Mars, Jupiter, Saturn. You need a telescope to discover the Uranus. Sorry, he discovered the Neptune, not the Uranus. The Uranus was discovered by William Herschel. He discovered the Neptune. It has a story. The Uranus was discovered, but the orbit was not right. So there was some perturbation, and they supposed that there is an 8th planet. And then it was supposed there is a 9th planet, and they discovered the Pluto. But the Pluto is not a planet anymore, it's a minor planet, but should be a 9th planet somewhere outside, but it's very difficult to discover. That was the lecture yesterday, and there was one mistake actually in this lecture. Here in this matrix the form was not good, so I thought this is not a good deduction, but it isn't. Okay, never mind. You can find this in Teams. Okay, I close this. Now, this is the practice. Practice, what is important? Determination of eigenvalues, this characteristic polynomial. Repeat, these eigenvalues are triangular and diagonal matrices that they are in the trace, in the spur, in the main diagonal. The trace is the sum of the eigenvalues, the determinant is the product of the eigenvalues. Some features about symmetric and antisymmetric matrices, and that's it. Now we will do something special. I will find an appropriate old example for eigenvalues, but we will continue. I didn't do it and didn't tell you, I haven't told you the theory, but I'm going to show you what is so-called diagonalization. All matrices can be transformed for a not all. Many matrices, many square matrices could transform to a diagonal form. That's practical. Okay, so now I'm stopping talking, and the problem is that it is not here, but it is here, fortunately. Okay, oh, that's bad. That's very bad. Oh. Okay. Sorry. Yes. Great. Yes. I hope that you are quite often visit these teams group, because everything is here. No. This is another group. Oh, no. It still comes in. Yesterday I didn't sleep so much. Here. Nah. I said open. Anyád. Why? Great. So Because I really hate this. I use what is the name? Nav. Okay, here, finally. After so many suffer and struggle. Okay, so there are nice examples here. Okay, let's start with this. And this is repeat and also okay. This is a repeat and also some progress. Yeah. So we have a matrix, very simple. And the question is the eigenvalues, the eigenvectors, determinant, trace, and diagonal form. Okay, let's start with this. So what is the eigenvalue problem? You have this matrix, this function, this transformation, this operator, whatever you want. So that was these statements at the beginning. So you can use anything; it's the same. For now, it's matrix. You are looking for a vector which are the same, and if you not consider a number, we are here in 2 dimensions, and this number is a real number. I told you it does not necessary to be a real number. It could be complex. It could be anything. It's more difficult. The teachers, who are mathematical students, learning algebra. It's more general, but it's not necessary for you. Okay, you have this. You have to solve it. Okay, what you will do? You looking for the result of this equation. What is this equation? It's nothing more than this is the form. This is the identical matrix multiplied by the lambda number. Okay, and You are looking for a non-trivial solution. The trivial solution is x00. When you multiply any matrix, you got 0, but you are not interested in. You are looking for the values when this statement is, this part is 0. This is 0 when its determinant is 0. So it means we have the A matrix, we have this value, I subtract the lambda, and also I subtract the lambda. And this should be 0. This is the characteristic polynomial. So this is the blah blah from the lecture yesterday. Only a few people could understand first the general stuff and then the specials, so the examples. It's not really didactic, but I'm not a teacher. Okay, let's calculate this. This means very nice. Okay, so this is 2 minus 4, 8. Okay, let's minus no. Minus 2, minus 8. Okay, so this is okay. This is nothing more than great. Okay. I felt A bit weird. That's okay. Phew. Actually, from this disturbed me. From this, you can just write. And then that's easier than this one. Okay, we have two eigenvalues. You are familiar with this, you can recall this. This is okay, that's nice. We have two eigenvalues. Now we need the vectors. Okay, so lambda 1 is 1. Then we have this matrix, and we substitute this 1 to this matrix. So this matrix is 1, 1, 3, 3, and I'm looking for an appropriate vector. This vector will be from both rows. So the subspace of these vectors, it's a nightmare. Actually, I remember that I use chalk here. So these vectors and this is more vector, so this is a subspace. This is one of the eigenspace. Okay, then you have a second set of vectors. It's 2 minus 5 minus 3, 1, 3, and minus 1. I'm looking for a vector that fulfills this equation, and it means and here it's interesting. No, it's okay. So x2 is 3x1. So the subspace of this second eigenvalue is vectors, where this is t, this is 3t, and t is a real number.
I thought this one was x-theorem. The x1 is equal to minus x2, but I realized they were different. What did you make it?
Sorry?
X1 is equal to minus x2 here.
Okay, what I... oh, thank you. No, that's okay. Here, I multiply this one. The first row will be You don't want to learn new Hungarian terms, I guess. This is, so this is it's okay. It's that's 2, not 1. And from the second row, you can get and then you divide 3 and move the 1 to the other side, so you got the same. Is it okay? This is also so this repeat. So this is how you determine the what is it, the eigenvalues and eigenvectors. So you are looking for the solution of this equation. This is the characteristic polynomial. You solve the equation. We are happy here because this is a 2 times 2 matrix. Usually a matrix which is n rank has n eigenvalue. So we can fix 2 times 2 matrices, 3 times 3, 4 times 4 is still possible, 5 times 5 has 5 eigenvalues, and this equation will be 5th order, and theoretically it has no closed solution, analytical solution. You must use a numerical method for this. Okay, this was the point A. That was the last semester. It's absolutely useless. Can you see anything on the table, on the board?
Yes. It's very faint, but it's okay.
Okay, so now I must take notes. Here. 1, 2 is 1 and 5. This was the solution of the A. With some instant heart attack when I missed the sign of the last number of the polynomial, the characteristic polynomial. Okay, so now we are here. Okay, the second point is quite simple. So what is the determinant of this? It's just 8 minus 3. It's 5. Okay, let's recall one statement. The determinant of a matrix is the product of the eigenvalues. That was a statement. And that's true. This is why I calculated the determinant, because everyone can calculate the determinant. Okay, let's calculate the trace. The trace is 6 plus 4, the main diagonal, it's 6. However, the trace is nothing more than the sum of the eigenvalues again. It's not a proof, not a deduction, but at least true. Okay. Sorry, this is in Hungarian. I will give you next lecture proper slide and I will explain. But you have a matrix. You know it's not painful. Plane shifting. There are a lot of suffer, a lot of work to do anything in a general matrix. But you have special matrix like snakes, permutation matrices, transformation matrices, and the diagonal and the upper and lower diagonal matrices. If you can do, you have a method for changing the matrix for diagonal form, then you won, you win. It's easier to deal the matrix and do a lot of calculations. This is again something I'm doing the board right now mostly, and we are learning about different formulas and materials and reactions and lot of things. No quantum mechanics and no computer calculation. No. At the beginning of the 20th century, many chemists became physicists. Did you see the Oppenheimer, the movie? You should, you should. You can download it, you can go. It's a very good movie. I mean, it's really good. But Oppenheimer did the A-bomb for the Americans, but he was not famous about the nuke. He was a project manager then. He made the theory of molecular bonds. Do you know what I'm talking about?
Yeah, I have watched it.
Do you know what I'm talking about? Okay, there is the water. There are two hydrogen and one oxygen. It's all difficult stuff. No, not water. Just hydrogen. You have one hydrogen atom, you have another hydrogen atom. You never see this on the Earth because they made a common electron cloud, and the electrons are not around the nukes, the protons. They are in both. That's the molecular bind. It's a covalent bond. It has theory. It could be calculated with huge computers. No, in a test of physics at the Utrecht University, you can calculate this. I mean the molecular, or not orbits, but probability and where are the, what is the shape of the electron, probability plot, and so on. So this is physics. This chemistry could be pure physics. And Oppenheimer did this one of this theory at the very beginning of this stuff. Also, John von Neumann. Do you know John von Neumann? John von Neumann? We called Neumann János. He was a Jew in Hungary, in Budapest, and in that time, his father was the family was quite wealthy, and he was excellent, very good mathematician. He was asked to learn something more practical. He started to learn practice. And then there was a law which restricted the number of Jews at the Hungarian universities. So he moved to Germany, and then he moved to the United States. And what he did, for example, the computers, the Neumann principle. The Neumann principle says all data, all program is in the same memory. It could be all computers, your computer, your notebook, supercomputers, your cell phones, everything in Neumann principle. It could. There was another approach. You have program somewhere else, and you have the data in different memory. But it's much simpler. And he was a good mathematician, and he was originally studying chemistry and started with chemistry and quantum mechanics. And he also did a lot of things about shocks, because it was necessary for the hydrogen bombs and nuclear bombs. So for me, it's okay that I'm explaining something mathematics for you who are chemists. I don't know what is in your mind. Did you learn any other mathematics right now? You in the second semester? Do you study anything?
We learn mathematical analysis in the second semester.
Yes, with the Parashkirai or with
Pop Market and Pecs.
Pop Market and who is the other?
Pecs.
Rebecca. Who is Rebecca?
She's in the chemical physics
Okay.
department.
Okay, thank you. So, this is the target, or eigenvalue will be in the spool, in the main, that's a German word actually, in the main diagonal. What we should do? We create a special matrix, invert it, and multiply the original matrix with it. Well, sorry, perhaps it will be more difficult than this one, but it will. So this X matrix is came from this stuff. This is a set of matrices. The simplest, if I say T is 1, then this is 1, this is minus 1, this is 1, this is 3. 1, 1, minus 1, 3. Okay, so let's invert this matrix. What's the determinant of this matrix? First, that's 3 plus 1, 4, non-zero, so I can invert it. Great. Let's do the inversion. First, I start with this argumentation. This is 3. I mean, the submatrix is 3. That's minus 1. Here 1. Here 1. That's the argument. Then there is this chessboard rule. It means 3 and 1 is the same. This is plus, this is minus. And now I do the transpose, and that's 3, 1, minus 1, 1. Okay, and then I have the inverse, that's 1, 4, because I'm divide by the determinant. 3 minus 1, 1. Excellent. Great. No. Oh, it's not visible.
Yes, I come to the one, so I can see it. But it's okay. I can understand.
Just a moment, I take grab other.
Is this a new matrix?
That's what I don't understand about the whole thing. The second one is the trace, right? This one, 3 plus 1, we're trying to find the trace. Okay. But then he did a sign of a determinant. You see what I'm talking about?
I don't know, man.
Maybe we're trying to find a determinant.
Yeah, he's trying to find the determinant, but is that a new matrix?
Okay.
The 1, 1 minus 1. Yeah, that's a determinant.
Yeah.
Okay.
And then that's the inverse?
Yeah.
Okay. I understand all of them, but I don't know how we got the starting matrix.
Yeah.
I'll abstain.
Sorry, this is awkward.
Yeah.
Very awkward. Yes, you can't read it or you don't understand?
I wanted to ask about the starting matrix. Is it a new matrix or you derived it somewhere from here?
You cannot read it, so I go for again. This matrix, this X, is created from these vectors. This is a lot of vectors, but the simplest is this. This is also a lot of vectors, but the simplest is this. So I put this vector here, also without restriction and without any stuff, discipline. You put together vectors to matrices and divide matrices to vectors. This was the linear space and subspace and everything. That's why you have so many stuff. So this is one matrix. If you want to get the diagonal form, you have to multiply the original matrix with the inverse of this matrix and the original matrix. I should have tell you yesterday the theory. I didn't, but I will. Just for practice, I think it's better and more useful to do this than anything else. I think. Okay, so here I start the inversion. Sorry for this. And I dropped the trash. I thought there are chocks. And this is not only one. These are my chalks actually. Once I came here with chalks, I think during the semester. So this is the determination. Actually, of the new matrix. This is not zero, so I can do the inverse. The inverse is done with the argumentation. The submatrix of this is in this corner 3, in this corner -1, in this corner it's 1, in this corner also 1. Okay? We have to check the signs. Here the signs are the same. Here it changes from minus to plus, and from plus to minus. Okay, so this is an inversion. Okay, then I do the transpose. This is the same, this is the same. The minus goes here, the other comes there. And then the final strike is to divide everything with the determinant. And this is now the inverse of the X matrix. And now the important stuff comes. I have to calculate this minus you cannot see. That's it. Let's start with this. Don't do anything now with this X. Okay? Let's see. 3 times 2, that's 6. Minus 1 times 3, minus 3. 3 times 1, 3. Minus 1 times 4, that's it. Okay, next one. 1 times 2, 2 plus 1 times 3, great. Then 1 times 1 plus 1 times 4, that's it. So it means that's 1, 4, 3 minus 1, 5, 5, and then the X. Okay? Okay, what was the X? Okay, 3 times 1 minus 1. 3 times 1 plus 15. Okay, that's quite interesting. That's bad. This is bad. No! No! Ooh, not at all. I was wrong. 3 times. No, okay. Ooh. 3 times 1, that's okay. And that's plus, that's fine, that's okay. Then 1 times 3 minus 3, that seems to be good. 5 times 1, 5 minus 5, and 3, no, 5 times 1, plus 15. Oh, that sounds good. I mean, seems to be good. 4, 0, 0, 20. Ta-da! So this is the diagonal form, and we have the diagonal form, and now we are happy. What are the eigenvalue of this matrix? Yes, of course. It's easy. The inverse of this is 1 and 1 per fifth. The determinant, so we can do a lot of things easy. So this diagonal stuff is a very useful tool. It's okay? Okay. It's also an upper triagonal form, so or trapezoid form. So it means what is it? The rank is 2. So that's nice. Absolutely not chemistry stuff, but if you have a numerical algorithm that calculates quickly determinants, calculates quickly, I don't know, matrix multiplication and anything, then you do this method, and there are different forms which shows you the cost, I mean the necessary computer resources of determining something from diagonal form or from matrix form. But this is not no, this is my stuff, so it's mine my field, not really yours. Okay, so we have less than 10 minutes. Ow. No problem. The environment is harsh here, so. Okay, I erase this. Could you work everything? Okay, great. Haha. Okay. Here, of course, it is in Hungarian, and we have 5 minutes. This is in the notes. I will not fix this. I have a matrix. We have a matrix. It's R burden. Okay, and this has 3 eigenvalues. Okay, and the solutions are there.
What value? Is it 14? No.
Which one?
14.
14, yes, 14, sorry. Sorry. Yes, okay. It has subspaces. And I say T is 1. So for example, 1 eigen there are more, just I use this one. This is not true, this is not true, this one. Okay, great. So, to diagonal form, I have to do this operation. So, first I need the eigenvalue of the X matrix. And of course, the X matrix is from this eigenvectors. Okay, so this is our matrix, that's great. Let me see. This is 35, 0, 0, then 0, 0, and then it's the determinant seems to be uh, 45. Okay, this is, we have 1 minute, so I keep completing. Okay, so this is minus 5, then 0, 0, then 29, then minus 7, 2, minus 7, 2. Okay, then this is 8, 1, 1. Okay, minus 5, okay. That's okay. So, let's do the calculation. Yes, the determinant is definitely 45. Great. So the inverse is so this is the inverse. However, I will continue the calculation. Matrix multiplication from the right, and this is free. Okay, so the original matrix was 1, then here 5 minus 2, 14, 9, 1, 3. I feel okay, it's fine. Okay, calculate. So, the okay, continue calculation from the right. Okay, and this is the original, that's minus 5, then 0, then 0. Okay, then 29, yes, minus 7, 2, 8, 1, 1. Okay, okay, so calculate. Yes! And we have the diagonal form. And that's it. 1, and these are the algorithms. So, sorry for the extra 4 minutes. And ta-ta! And thank you very much for your attention and coming. I hope you think this useful. This is I think that you think that this is a useful method. Then I'm pretty sure I will ask this in the test. You will have practice in this. and I will tell you when you can use computers. For example, this page and when not. Okay? Okay. Thank you very much. Thank you.
Bye bye.
Bye bye. Have a nice day. Have a nice weekend. Enjoy the sunshine. Bye bye.